purpose of my presentation today is to give you an overview of what is called physical attacks against cryptographic implementation in embedded systems. So we're talking about attacks that use some real physical means as opposed to purely software exploits. We will, both subjects overlap a little bit, but we'll focus on the physical part of the things. So I'll start with an overview of the various attacks that are known as of today. I'll focus on two types of very common and simple attack, which are the timing attack and the fault injection attack. And I'll have a detailed example on how do you mount a fault injection attack on the public key algorithm called RSA. Then I'll continue with giving some target security performances for standard algorithms such as the AES, the RSA, or the elliptic curve algorithm. I'll look at a software implementation of these, but actually this figure would also make sense in a purely hardware implementation of these. And I'll finish with a couple of countermeasures to defeat the hardware attack. So essentially what we're talking about today is electronic embedded system that need to perform cryptographic function for security reason. Be it a payment card, a payment terminal, a wireless router, a smart power meter, what's called smart power meter, so a power meter that has some ability to communicate, gaming console, digital TV, voting machine, you name it. All these devices implement cryptographic algorithm, and this cryptographic algorithm can be attacked. And we'll see how does that work. So cryptography is something that is absolutely key in embedded system. I mean, there's no way you can avoid cryptography in any system that requires user authentication, software integrity, access control. In your day-to-day interaction with embedded system, you are very often exposed to cryptography. Viewing a web page, something as simple as viewing a web page, is now more often than not using HTTPS. And HTTPS is a protocol that use cryptographic algorithm. So cryptography is everywhere in embedded system, and it is a safe method from a mathematical point of view. So you may hear here and there about cryptographic algorithm being attacked. Well, actually, the cryptography itself is really safe. Safe means it's impossible to break, or the time it takes to break is more than the reward. And if you use standard algorithm, so if you use things that are proven by the experts, and if you use a key size that is large enough, then you're safe. So what is not safe is its implementation in embedded system. When you implement an algorithm, a cryptographic algorithm in embedded system, you have somehow to cut corners. You cannot implement it in the most safe way all the time, because that would require redundancy, and redundancy requires computing power, and computing power is a resource that is scarce in an embedded system, especially those that run on battery, but even those that run on main power, you don't have full credit for computing power. So you need to somehow make trade-offs, and this trade-off have consequences on security. So the biggest source for bad implementation of cryptography is key management. So the way you move the value of the key across your system, the way you store the key into memory, even at the protocol level, the ways the keys are generated or created, that is the biggest source of weak cryptographic implementation. Now, if you've done this properly, the next biggest source is that your hardware itself leaks information. We'll see how and why is that. But the CMOS transistor leaks information. And then, that is called, in terms of attack, that is called the side channel attack. So exploiting side channels to guess the secret key. We'll look at this in detail. And then the third reason for implementation being not safe is there are ways where you can modify the normal behavior of a chip. And when this normal behavior is, when you're not in the nominal behavior of the chip, then some weird thing can happen, and that is the source of what is called fault injection attack. So bad key management, side channel attack, and fault injection attacks are the three primary reasons why cryptographic implementation fail. So let's have a little bit of an historical perspective. In the 1980s, so these are the 20th century attacks. In the 1980s, prepaid cards for public phone, which were essentially memory cards, were used and were attacked with a very simple mean. It was just a scotch tape on one of the pad, and this scotch tape prevented the stop counter decrease, which means that you had no stop counter. Later in the 90s, it was something a little more sophisticated where you lowered the supply voltage to block the retry counter, and then you had infinite pin trials. The pay TV is really the area where, that's public phone. That's a thing of the past, by the way. Public phone, you don't see those much often now. That's payment card, and that's pay TV. So pay TV is the hottest area in chip security. Because this is the area where it's easier to, once you have broken the algorithm, it's easy to benefit from the service without being detected. So some people started to do fancy stuff with, the idea was using the test mode of the chip, because in the test mode of the chip, you would have access to a lot of information that you don't have in the normal mode. So the goal was to access the test mode, and these clever guys managed to do it with invasive attack on hardware fuse. So basically, they modify the value of some hardware fuse, and were able to enter the test mode. And a guy by the name of Christopher Tarnowski started to use micro probes to snoop the bus. So the device being depackaged and delayered, the device being functioning this way, he was micro probing with a microscope and probes to actually read some values in memories or buses. Later in the 1980s, emerged the biggest family of attack called power analysis and differential power analysis. So another smart guy by the name of Paul Kocher invented the device and invented these attacks, although they were already known to some people, but at least he patented the countermeasure for these attacks. And we'll see what that is in detail. So that's 20th century. The more recent attack, I've tried to establish a hierarchy of this attack here. The one here in red are those that are at the frontier between hardware attack and software exploits. So they're basically eavesdropping, which is the simplest way of trying to guess. So that's a very old way of attacking a hardware system. Man-in-the-middle attack, replay or relay attack. So these are, I won't talk about these much in my presentation today because they're somehow at the limit between software exploit and hardware attack. The further we go down the road, the bigger is the cost and the complexity of this attack. Therefore, the attacks, the type of attackers, so these ones are pretty much everyone, including students. Then these one in blue and yellow would require some expertise, tough expertise, and some level of equipment that is in a couple of tens of thousands of dollars. And then the one in red here are only available to very large organizations that can hire experts. So most of the time when you have an embedded system in a product, you want to be student-proof and expert-proof. You can't be large organization-proof, and that often doesn't make business sense. So the category that we're going to look at in detail today is side channel and fault injection. So in side channel, you have timing, simple power analysis, differential power analysis, and electromagnetic emanation analysis. In fault injection, the main one are power, clock, temperature, and laser. And then the invasive attack could be by means of optical microscope, electron microscope, or focused ion beam. So let's look first at side channels. So the principle of a side channel attack is to make use of some side channel. And a good example is the MI5 in the Egyptian embassy in London. At this time, they were not using an electronic embedded system, but rather a mechanical embedded system. And this system, think of it as the round, like the round in a safe. When the round moved, they make some noise. So what the MI5 did is they put a microphone in the room where this cryptographic machine was used, and they could listen to the noise of the metal round clicking, and from this noise they could guess the secret key. So the idea in power analysis is the same. You look at the power consumption of a chip, and by means of statistical analysis of this data, some quite complex and fancy statistical analysis, you can guess the secret key. And the goal of the attacker is to guess the secret key. There's no other goal. Once you have the secret key, you pretty much know everything. So the timing attack relies on the monitoring of the time taken to execute a cryptographic algorithm. And all these other single power analysis, differential power analysis, and electromagnetic analysis, they rely on the power needed to execute a cryptographic algorithm. And from this power analysis, you will identify the secret key. Fault injection attacks are based on an unexpected environmental condition that reveals the internal state of the cryptographic implementation. So we'll see how it works in detail just after this slide. But basically, the idea is if your chip is not operating in its normal condition, you can disrupt the calculation of a cryptographic algorithm. And if the calculation is disrupted, you have access to what is called a faulty result. So a result of the calculation that is not the expected result. And with some clever cryptographers, the faulty results can help you get back to the secret key. Because you have interrupted the calculation, and because the calculation wasn't completed, you have access to a number that is a faulty result, and this number can help you get back to the secret key. So the difficulty in mounting a fault injection attack, well, the hardware difficulty is how do you get the chip to operate in its unexpected environmental condition. So temperature is one. So temperature outside of operating range means that the content of a non-volatile memory, such as a flash or an E-square PROM, can be modified. And you can even stop the NVM read operation. Strong electromagnetic fields, X-ray or ion. So that is well known to people designing for airplane or satellite electronics. These people try to avoid as much as possible what is called SEU, single event upset, or SET, single event transient. Is basically a neutron modifying the value of flipping a bit somewhere in the chip. Well, the attacker would do exactly that. He will try to flip a bit somewhere in the chip, and he'll hope that this flip bit propagates through part of the design. Voltage glitch is definitely a very famous and probably the easiest way of mounting a fault injection attack because it doesn't even require any privileged access inside the chip. So a voltage glitch on the power supply or a frequency glitch on the clock. And then laser, although this one is much reported in academic publication, and there are lots of articles in attack based on laser or other light source. It's not that easy to mount because it requires a depackaging. And depackaging is already a step that costs some money. So if you can do stuff without depackaging, like voltage glitch or like side channel attack that we saw previously, that's a much easier attack to mount, and the easier the attack, the more attacker you get. And then the most sophisticated attack are invasive attack. I won't talk too much about these because also they've been reported quite a bit. Just a nice picture of someone who has actually modified a circuit in order to mount his attack. So shorted a line and added another connection here. I mean, cut a line here and added a new connection here. So there are a number of things you can do. The simplest is imaging chips. So some people are in this business for competitive analysis. Some other would be willing to really reverse engineer. So optical works for 0.18 and up. Then below 0.18 you need an electron microscope. Micro probing is also something that attackers do. The equipment needed for micro probing is in the $100,000 range, though, so it's not a student type of attack. And focus ion beam is even more expensive and more complex. With an invasive attack, you can pretty much do anything, although there are ways to protect against some level of invasive attack. At the end of the day, invasive attack always win. So let's get back to the fault injection and side channel attack, which are the main topic today. So how does that work in reality in a chip, and where to attack? So here we see some different what's called attack vectors, or different ways to attack. Voltage glitch would be simply on the pins or pads. Same for clock glitch. Signal monitoring and standard IOs will be monitored in all the attacks. So you, of course, use all the available signals that are available outside the chip. And then you can also have access to the surface of a chip after depackaging. So depackaging is not that big of a deal in most of the package, except the BGA package. The BGA package makes it much more complicated to depackage. Let's start with more detailed review. I'll review the timing attack and the fault injection attack on RSA. So the principle of operation, everyone understands that the computation time depends on the process data. A way of looking at a crypto algorithm is a black box that blends a key with a message. No matter how it blends it, end of the day you have a key and a message. So the secret key is part of the process data. So if you record carefully the process data, you can guess the secret key. So what you do is you encrypt many random messages with the same secret key, and you do a statistical analysis of the computation time. It's sort of a dreadful attack because it can be done by remote. Some people demonstrated that they were able to measure the computation time of a server, even if there were several routers in between, and even if they didn't know the latency of each router. Because they're doing statistical analysis, they could average the latency of all these routers and therefore mount a timing attack from remote. The countermeasure, well, the first one that crosses your mind is you can try to compute in constant time. But that's not good, because if you compute in constant time, you'll always get the worst execution time. So your security will be better, but your performance will be less. A better idea is what's called blinding. Blinding is the idea to blend the message with a random number before processing it. So blinding is really the very efficient way to defeat timing attack. And the open source crypto library, the popular OpenSSL, that are used by a lot of cryptographers, at least for computing power in the high range, now requires a blinding. So let's look at RSA, fault injection on RSA. The principle of the RSA algorithm is you have two keys. One is a public key. In my example, it's E, and I took the number 17 as an example. And the other is a private key, D, that is 2753. So in order to encrypt, you execute this formula, so the plain text to the power of the public key modulo n. And to decrypt, you do the same thing, but with the public key. So you see, the calculation is quite simple, but in order to implement it, you complexify it a little bit with what is called the CRT, the Chinese remainder theorem. And the CRT speeds up the calculation by 4x. However, it introduces a security weakness that we'll see. So the idea with the CRT is, instead of doing all the calculation modulo n, which is called the public, the modulus, which is usually a very large number, you perform the calculation modulo p, then modulo q, and you obtain the formula modulo n. Well, the problem of this is, here's what you can do. you're going to induce a fault in a hardware register at the precise time where you are doing the calculation with one of the modules. So you're first going to monitor the I/O and the power consumption. You're going to look for two high activity periods that are visible in here. And these two high activity periods will correspond to the calculation module Q and the calculation module P. And you're going to try to fire your laser or your microwave beam or your voltage glitch or whatever during one of these two, which is pretty easy because they are very identifiable. And the cryptographic theory will tell you that if you have disrupted the calculation module P, then you're able to get back to P. And when you're able to get back to P, since you have N, then you can easily get back to Q. See here in that example, maybe it was a little quick for everybody to get it, but you're calculating your RSA using a method that saves you computing power. And at some point, you are introducing a fault in part of the calculation. And cryptographers have made this calculation for you, and they know how to get back to the secret key once you know this faulty computation. So in theory, you don't need to even understand these calculations. All you need is to apply the result, which is you can get Q is the greatest common divisor between the good calculation minus the faulty calculation modulo n and n. So from Q and n, you can calculate the private key. So this works very well, and this is an attack that can be mounted very easily, and that is not so easy to defeat. So fault injection, I mean, it's a real thing, and it can break a strong cryptographic algorithm very quickly. So they are countermeasured, though, and it's one of the first attacks based on fault analysis, and there are a number of more complex attacks on the same principle as of today. There are some countermeasures. So at the algorithm level, same idea as the blinding, that is add randomness to the private key and public key, and also check any calculation before you release them. So in order to avoid faulty results, you check the calculation, and if it's not the right calculation, if you're not able to get back to the ciphertext from the plaintext, then you don't release that on the bus. There are also chip-level countermeasure. A shield on the top metal layer will prevent the laser attack, and a power supply with built-in filtering and also a glitch detector would help a lot. I'll go quickly on the recommendation for AES, RSA, and ECC software library. The idea is that, okay, you have open source cryptography that is great, but that has not enough security and that has not enough performance. So you need hardware acceleration and you need software countermeasure in the security. It's easier to implement the countermeasure in software as opposed to hardware because there are new attacks every 3 to 6 months. So if you want to update your hardware, and a software implementation is much better. So I'll skip the performance, but you'll have this figure in my presentation. So these are the recommended security features and performance for a typical implementation of AES. I choose the figure on the Cortex, the ARM Cortex processor, but the same would apply to other processor, RSA and ECC. So every time you get the throughput, the memory and size, and the security requirement. I'll finish quickly with some hardware countermeasures. So random number generator, this is the number one most critical part of a secure SoC. Most of the time, embedded systems don't have a proper RNG. They use what is called pseudo RNG, so basically a LFSR. If you have a very good quality of a random source, then all the countermeasure that we looked at, randomization, the blinding, they become very efficient. So the quality of the randomness, the so-called randomness of the bits that you generate is key. The power supply and the clock management is also key. So a circuit should be properly powered. You should get your power supply should be able to detect if the attacker is trying to go into the non-authorized zone of power. Same for the clock. You can add jitter to the clock. That works very well. So that defeats timing attack. by introducing jitter from your random source. If you have a jitter clock that is random, it's very difficult to measure execution time. A voltage glitch detector, it would be an analog cell that has the ability to detect large spikes in the power supply. And large spikes in the power supply can come from attackers. Temperature sensor, that's an obvious one. A light detector, although that is not so easy to implement. And a shield, which you have a block diagram here. So a shield is basically a sensing mesh on the topmost metal layer of your chip with a pseudo-random sequence injected somewhere. So if the attacker tries to cut and strap this active shield, the pseudo-random sequence would be interrupted. Okay, so I'll finish. The message I want to deliver this morning is basically that cryptography works, but cryptography needs to be protected. If you don't protect cryptography, well, it's just like if you haven't used them. So it has to be immune to all known fault injection and power monitoring attack. And you can hope that if you're already immune to the known attack, the attacker will have a hard time and they'll take care of someone else's chip and not your chip. It's adding security feature in an SoC design has some consequences on performance and area, but that's largely manageable. So we're not talking about a 2x increase in size or drop in performance. It's often measured in single-digit percentage of increase in size and performance. So NVIDIA comes from the smart card industry that has been one of the first industry to use these hardware countermeasure, and our job is to adapt the solution design to the smart cards and adapt that to large and recent SoCs.